Hello again, I was a bit late. It's pretty difficult for question 1 actually. So both need to be strictly greater to move forward to the next one. And we're always gaining experiences and we're always like decreasing energy. So like our initial energy has to be larger than the sum of all energies, and our initial experience has to be greater than something like it has to be so that the accumulated sum is always greater than 0. So that's it. So for example, for this, we need initial energy 10 or like 11, so we need 6. And the I'm thinking about what's the easiest way to code this experience part. So maybe I just iterate through. Make it shorter. Energy. Let's put an I to initial so that I can set here. So we would need to train on our energy if and only if the energy sum is greater than or equal to the initial energy. So if this is negative, we don't need to do anything for this part. If this is positive, just use an if else instead of writing it as an expression for simplicity. And current experience is like experience. Do I need a +1 here? That's what has been confusing me the whole time. Is because if they're equal, then this is 0, but we still need a 1. And like, what else? That's awkward. So energy part is fine. So here we need 5 or 4. No, never mind. Like energy part we need 6 because 1 plus 4 is 5. And then here it's alright, and then we need 1 additional training. So what went wrong here? Is this. So we group them in pairs and we start by, so like the longest is always better than shorter ones. And for that we pick as many numbers as we can, which means all the pairs plus possibly 1 single largest integer. And then we form the first half by like just ordering them. And there are some special cases. For example, if all we have is 0, then we have to use something non-zero. Just count them first. And I'm adding everything we can pick from a list to a list. And then I can sort it later. Okay, is this correct? this is like dealing with all the pairs. And then I'm going to iterate through it again to pick the largest one. And I need a singleton somewhere. Yeah. I still cannot remember if there's a default value for max in like whatever version of Python. Okay, I think this makes sense to me. So it's guaranteed that so there's a special case where we didn't pick a singleton here because it's part of a pair, but then there's nothing in the pairs. Then the only thing we can do is to just pick the largest number. This is the case when okay, so either there's no pair or the largest one in pairs are zeros. And we just pick the largest one. And we need to return it as a string. So if that's not the case, that means, so first of all, we have pairs, and secondly, the pairs are not zero. Then the only thing we need to do is if it's not can That's, again, pretty long code for question 2. Okay, it's a binary tree with unique values, and we have an integer start section. Why? Okay. I was gonna ask why we need the unique values. So we build a undirected graph and we do breadth first search. That's like easier than question 2. It's probably the same anyways. Okay, whatever. And we also need the other way around, which is a lot of things to type. And we're asking for like rounds. Okay, so let's just use a start in 0. And as usual, we have a sin just to keep track of how many things we've seen already. Q. I should put an iterator here, right? I don't remember actually. Left. What am I doing? So this is a standard breadth first search, so I'm not explaining anything. That's it, right? Subsequence of array and sum of its elements together. We want the kth largest subsequence sum. Counting duplicates. So, okay, so we might have negative numbers, so we cannot just sort them and like drop smallest. So we sort of need to, I'm thinking that we need to consider the positive parts and the negative parts separately. Because the largest ones, the largest subsequent sums would be the ones involving only the positive parts, and then the smallest one would be the ones only involving, is that true? Well, in between, it's not clear whether like partial positive sum or like mixed sum, which ones are larger. So it's not exactly like that. I need to think again. And what's the range of? So n is quite large, so our algorithm need to be like, cannot be n squared, can at most be n log n. But for k, we can possibly take a square because it's only 2000. Interesting. So what if we only have positive numbers? If we only have positive numbers, then sort of some combinatorial terms. Can we iterate through all the possible subsequent sums? Like by some popping-ish things? So like, what I'm saying is we define an ordering on all the subsequences. It's ordered first by sum and then by something else, such as like lexicographical order. And then it's like an enumerate permutation type of problem. So for example, if we're at a certain stage, we're looking at one subsequence. How do we find the next largest subsequence? The next largest one would be something that's slightly smaller than it, which means either we can add like a small negative term or we can pop a small positive term. I'm thinking like we have two heaps. One is a max heap, one is a min heap, but maybe that's not enough because or is it enough? So how do we decide whether we want to pop the smallest positive integer or add the largest not the largest, is the largest negative integer. Maybe let me try to write some comments and see where it goes. Storing. So we need something like 4 because we also need to store things that we're not using. Are we ever going to use some positive integer that we throw away? Yes, we will, because say for example we have like 8, 4, 2, 1, then we're basically enumerating like binary. But this isn't a question like that. And then the question is like, maybe we need the largest unused one. Or I just give up and use like sorted containers where I can get from both sides at low cost. And I need a sorted list because there might be duplicates. And the same for negative numbers. Okay, now it's the interesting part. So I'm thinking about like duplicates in the original sequence. We need to take care of it somehow because otherwise um, it's complicated. Otherwise, we might get into some. We need to break the tie. That's all I'm saying. So maybe I first turn it into like I add the index to it too. Actually, if I just put like list enumerate, is it already that? I should try that out later. Define and ordering on all subsequences by first by sum by hope I spelled it correctly. And this should be reversed. Yep. So this is like a second order lexicographic order. Like for each individual subsequence, we only consider like the normalized sorted form, and then we compare them lexicographically. This is guaranteed to break tie. And it's dominated by the sum, so we're getting the correct result. So I'm thinking about just enumerate like several possible neighbors and choose the one that makes the most sense. What would be it? So we have some positive part, we have some negative parts, we're swapping a bit in the middle. So we have several options. Or add, just is it actually? Is it? It probably isn't because we might need to swap more than just a few. Again, in the example of like 8, 4, 2, 1. So like after 8, the next thing we want to get is 7, like 1 plus 2 plus 4. But then in that case, we're still dropping the smallest positive term. I'm thinking, does it ever make sense to drop some positive term that's not the smallest? Yes, because if we have a lot of other positive numbers that are not in use, we might let me just write some example. Say we have 8, 4, 4, 2, 1. And we're currently at like 8 plus 4. And then the next smallest would be 4, 4, 2, 1. I think. Which isn't done by, yeah, so this doesn't make too much sense. How did we enumerate the next largest permutation? I think it's like some problem in the first 50 problems. And I didn't pass it. It's funny. So the idea is this, like currently my idea is basically the same. We're doing some kind of depth research on all subsequences, is it? So another idea is, again, we deal with like positive numbers and negative numbers separately, and for positive numbers we enumerate like subsequent sums. For negative numbers we also enumerate subsequent sums, and then their combination would be, yeah, we can enumerate the pairs. That sounds about right. I hope I explained myself clearly. So like we only need to do with the case where like all numbers are positive, then that can be done like more easily by help by some combinatorial, or actually just like max or min heap. No, maybe not. Well, let me think. So to make myself clearer, so I want to get like the separately largest case sums of positive numbers and also like smallest case sums. Do I mean largest and small? This small negative numbers and sort all pairs of this. That's why we can have like k-square. And we can do these two cases presumably with one auxiliary function. But I need to figure out how to deal with one case first. What's wrong with the internet? Is there something like that already? No. This question is like on a different scale, so I cannot really use it. Binary search. Can I count easily how many numbers, like how many subsequents will sum to a greater number than my x? If I can do that, then I can binary search on the kth largest sum. It doesn't really seem like binary search reduces anything, I think. So again, this example of 84421. I'm picking this because it's like almost binary, but not. Like almost a geometric progression, but not. So write it here. The first idea is to binary search on K. Not on K, but on like which. No, actually I cannot binary search because I need the K sums. It's not enough to know the kth sum, but I need all of this K sums. So I cannot binary search. Find some way to find the next largest subsequence sum. That seems to be the only thing that makes sense. Suppose at any given moment we have like what we're including in the subsequence and what's excluded. If everything is in our subsequence already, we just drop the smallest, that part is clear. But if both are non-empty, so if everything is excluded, then it's also clear we're done. Otherwise, if both parts are non-empty, we need to have like, we need the minimum difference between a sum in the used part and the sum in the not used part. In order to do that, difference I'm still thinking that a sorting based algorithm would be better. But let me finish this sentence first. Between a sum of how can we sort it without actually sorting it? Because as usual, like when we see the kth largest, our first impression is like we need a min hit somehow. But then like storing the whole thing would be too much. What if we just enumerate and hope for the best? That doesn't make any sense. No, we cannot enumerate all the possible subsequents. So this don't really make sense. I guess my rating isn't too high because after all I have a wrong answer on the first one. But not that bad either. Okay. Whoa, that's impressive. Good job if you're watching this. So like essentially for this, we need to keep track of all the possible sums, which is potentially like exponential. So it doesn't really make sense. Like this is undoable, which means I need some other idea. But I think like this part is correct, like dividing them into positive and negative parts is correct. At least it reduces the problem. Then for this part, so naively, I'm tempted to think that, like, how do I put it? So suppose we sort it first from largest to smallest, and then we always want to like try to add or drop the last elements first before like consider dropping the previous element. So like if we're fixing the first, say, I numbers and dropping the remaining n minus I numbers in some order, then like moving this i's would be invariant to um, the ordering. If I'm making myself clear. Like within the fixed I, the dropping and adding might not be just enumerating all the like 2 to the n options, but if we're dealing with each I separately, then it's okay, which means we're doing at most like 2 to the log k many enumerations. So let me try to just implement that first. Maybe. Is it true? Is it true? Say, for example, we have 4, 4, 3, 3, 3, 3. Or like a lot of twos. could it be the case where I'm trying to say, could it be the case where like dropping this is larger than dropping this? It is the case. So what I just said was just wrong. So it's the same as finding the case smallest because we can remove the case smallest to obtain the k largest. And it's somehow easier to reason about. And for the case smallest, can we somehow do better? So like somehow a brute force option, and like considering that k is not too big, is that we have a list of items that we're currently considering, and we keep track of all its sums, and then we add additional ones to it. That's very brute forcey, but let me try maybe. So first of all, we can bound it by that seems to be what I was saying, like what I excluded previously. Like what I was saying is that by enumerating the last log k elements, we can get the k smallest subsequences, which isn't true. but still we can bound by like k here. We only need to consider the, like, it's bounded by the largest of, I don't know what I'm saying. It's bounded by k, but then we still have the exponential there. So is it possible to find the k smallest subsequent sums of 2000 numbers? Is it doable? I mean, it's doable, but like how? Does it make sense to enumerate in the order, like picking one number, two numbers, three number, four, all the way to something? But then again, I might be able to come up with some counterexample to this, where we really need to actually, like, for, no, I'm sorry, this. This feels like, I feel like I have a k cube idea, or maybe not. For each number, we add it to the sums already existing, and then we only pick the first k. That doesn't make too much sense, but somehow I want to try. If I extend it, is it still sorted? Let me hope that it implemented it in a reasonable way. Doesn't make any sense at all. Maybe. These are all positive numbers. These are the sum of all positive numbers. These are the case smallest ones. And if we want the case largest ones, we just like subtract it from in this, I don't need to do anything. It's just like helper. The kth, let's actually do. Okay, I cannot extend it. Okay, when I used add, it becomes, so there's something weird in this. I expected it to remain a sorted list, but apparently maybe after slicing it's no longer a sorted list. Sorted containers. Sorted list. Where's sorted list? Here. This is too heavy. I don't want to add the first one twice. So the question is, why is there a -2 here? This should be 6, right? Okay, so we're effectively adding each number twice, which we shouldn't. How do I deal with that? So all I'm doing here is like for each new number, we can potentially add it to a previous sum. Amazing. Are we like getting one more zero than there actually is? Or actually one less zero? So I also need to include this like positive sums and negative sums. But I need to remove a zero somewhere. I would have thought that there should be a zero here. But apparently there isn't. Where do I put the zeros? Like we want to have actual zero, but also the fake zeros. Like there's one fake zero globally. But there might be like real zeros that are like zeros as sums of subsequences. How do we deal with that? So for simplicity, I put a zero here. Maybe I shouldn't. And then we wouldn't have like fake zeros as results of helpers. And then we can add one additional real zero here. And apparently we need to do something about this. Sorted leaves has no attribute sort. Let me put a list here just to make things simpler. And then I don't need a list here. And all I'm saying is here I need like one additional. That's quite some patches. So where does this zero come from? So the bottom line is that the zero should only come as either what am I doing? Either as like individual element from plus or as a combination of two. And this stands for like not picking anything altogether. And if I'm not picking anything here, we get, let's see, I have 2 minutes. Maybe let me just submit it once and hope for the best. Oh gosh. Actually, why do I have 2 4s? Yes, I have 2 4s. I see what the problem is. It's not enough to have just the cave. even if we take combinations. But this idea is mostly correct. I guess I don't have enough time to finish it off, but it was a nice contest.